Our next order of business is to look at the end behavior. The end behavior is when x approaches positive infinity what is happening. Trying direct substitution, we have a very large number on the top and a very large number on the bottom. And what do we know about this? This is L'Hopital's rule. So let's do it. This gives us the limit as x approaches infinity of 2x divided by, changing this to a x plus 1 to the 1/2 power and using the power rule, we're going to have something like this, which we can do a little bit of algebra, take the reciprocal and multiply, and we end up with 4x times the square root of x plus 1. Now, as x approaches infinity, you have infinity times the square root of infinity, but that is not indeterminate form. A large number times a large number is still a very large number. So as x gets large, the y also gets large. So if you're keeping track, the end behavior is going to be something like that. Next, we've got our first derivative information, and we have an option. We can either use our original function, or we can rewrite the original function to be a product rule instead of a quotient rule. That is your option. I am going to take the product rule option here. I'm sorry, I'm going to take the quotient rule option. So we have the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. What are we going to do with that? Well, hopefully we can find some things to simplify. Hopefully we can factor something out. I see a fraction here, and I'm going to do my fraction trick, and I'm going to put in a 2 over 2 so that I can factor out those fractions. So factoring out a half, and I think I'd also like to factor out an x and an x plus 1 to the smallest power, which would be a negative 1/2. So what does this give us? We have a 1/2, an x, and an x plus 1 to the negative 1/2. What do we have left? A 2 times 2 gives us a 4. An x plus 1 to the positive 1. Note this times that. You would add the powers to get a positive 1/2 there. Here's our minus. We factored out the half. We factored out x plus 1 to the negative 1/2, and we factored out an x. So we're left with just an x there. And this is all divided by x plus 1. We can do better. We can factor some more. We can work this out a little bit more. I'm going to rewrite it by taking the x plus 1 to the negative 1/2 down to the denominator and combine it with the x plus 1 to the first. So we have x times, looks like a 3x plus 4 in the numerator divided by, we have halves in the denominator. We have x plus 1 to the 3 halves in the denominator. Now we can look for our critical values. Critical values occur when the numerator equals 0 or when the denominator equals 0. So let's look for what makes the numerator 0. How about x equals 0 and x equals -4/3 for the numerator? And then for the denominator, how about x equals -1? So those are values that we should consider for our number line. We've got our number line with our first derivative and our equation. So here is -4/3. Here is -1. Here is 0. Now, one thing that we would like to remember, so that we don't have to work harder than we need to, is the original domain of the function. Notice that the domain goes from -1 to infinity. So when I look at this number line, really everything over here doesn't matter because it would give us imaginary numbers in our original function. It's not part of the domain. So I can get rid of all of that, and really now I only have to check 2 test points. My first test point is going to be a -1/2. Into my derivative, I have a -1/2. 3 times a -1/2 is -3/2, plus 4 is positive. 2 out front, that's going to be a positive. A -1/2 plus 1 is a +1/2. Raised to a power is still positive. So we have negative, and we are decreasing. Then let's pick a number to the right of 0. How about 10? +10. 3 times 10 is 30, plus 4 is 34, is positive. And 10 plus 1 is 11. To the 3/2 power is still positive, times 2 is still positive. Positive divided by positive is positive. So we have an increasing function from 0 to infinity. Now, we can say we have a local min. And it would be correct to say, since we're only decreasing then increasing for the whole domain of the function, that this would also be an absolute min as well. All right, now we get to do our second derivative. You know, it would probably make sense to distribute this x so that we don't have to do a product rule for our second derivative. So I am going to work with 3x squared plus 4x divided by x times x plus 1 to the 3/2 to find my second derivative. All right. So f double prime of x. Applying the quotient rule, derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So now we have to factor this and find the zeros here. So let's see what we can do. First, I think I'm going to simplify a 2 and a 2. That's it for that. Then I'm going to look and see what I can factor. I notice that there is an x plus 1 to the half that we can factor out. And I think that looks like that's it for now. So x plus 1 to the positive 1/2 times what's left. Well, we've got 6x plus 4 times 2 times x plus 1 to the first. Note that the powers, when we add those up, we end up with 3/2, which is what we want, minus 3. That x plus 1 to the 1/2 has been factored out, times 3x squared plus 4x. And then all over, since we're squaring this, 2 squared is 4. That x plus 1 to the 3/2 squared, we would multiply those exponents. So we have cubed. Okay, from here, we can decide how we want to combine our like terms. I think we're just going to have to distribute some stuff out and then combine like terms. For this big parentheses, for the x plus 1 to the 1/2, we can combine this with this and get rid of one of those terms. So let's distribute up top 12x plus 8, multiplying in the 2. Next step, we'll FOIL that. Let's distribute that 3. We could do that and that. All over 4 times x plus 1 to the 3/2 minus 1/2 is 5/2. Distributing out this first set of parentheses gives 12x squared plus 12x plus 8x plus 8 minus 9x squared minus 12x all over that denominator stuff. Combining like terms will give us a 3x squared and then an 8x and an 8 and the denominator. At this point, we're looking for possible points of inflection, and we need to know if the denominator is 0. I'm thinking that doesn't look like it factors, so I'm going to just do a quadratic formula real quick. You can sing it if you need to. And since 3 times 4 is 12 times 8, that is bigger than 64. That means this stuff is negative, meaning we only have imaginary zeros, so no zeros from the top. What about the denominator? Do we have any zeros from the denominator? Well, there's an obvious 0. That is when x equals -1. Great. So note that if I take a look, since there are no zeros from the top, I can also take a look at this and note the top is always positive. So I do my number line, look at our second derivative. Here is -1. Everything to the left of -1 was undefined. Taking a value to the right, such as 0, gives me a +8 up top, and then a +4 times 1, which is positive on the bottom. So that is concave up. Let's put all of that together. Scrolling back up, seeing where we've come. So we have our domain. We know there's a vertical asymptote at -1, a y-intercept at the origin at 0, 0. The end behavior to the right, we know it's going up to positive infinity. A function that decreases, hits a minimum at 0, and then increases again, and stays concave up. So the graph that fits this description looks something like this. Vertical asymptote, 0, 0. Said it was from here, decreasing, concave up, minimum, increasing, concave up to positive infinity, something like that. And that is the end of the problem.